about recalling the rules of Surds and using it to simplify complex expressions with Surds. This includes being able to rationalize accurately and solve problems involving Surds. This is GCSE knowledge, but you need to be really confident in this in order to progress in A-level maths. I will go through multiple examples, so feel free to pause whenever you want. The first thing I want to make clear are the rules of Surds. So which of these statements are true and which are false? So I have root of a plus root of b is equal to root of all of a plus b. So this statement is unfortunately false. So we can prove this using a counter example. If we let a be equal to 9, so root of 9, and b be equal to 1, so root of 9 plus root of 1, that is the same thing as 3 plus 1, which is equal to 4. But if I square root 9 plus 1, I get square root of 10. Do you see how these values are not the same? So here's an example where it doesn't work out. So this is a counter example. So this statement is not always true. So please do not simplify using this rule because it will not work out. In a similar manner, this statement is also not true. So if I use the same values, root of 9 take away root of 1 is 3 take away 1, which is 2. But if I do square root of 9 take away 1, I get square root of 8, which is obviously not the same thing as 2. So again, we're getting two different values when we substitute a equal to 9 and b equal to 1. So this statement is also not true. Root of a times root of b, this does work out. So it is the same thing as square root of a times b. So you can always simplify vice versa. Square root of a over b is the same thing as square rooting each one individually and writing it over the fractional sign. So square root of a over square root of b. Okay, in this second column, root of x squared plus root of y squared, because you're squaring each term and then square rooting it and then doing the summation, it is the same thing as x plus y. So this statement does hold for all values of x and y. Okay, root of x squared plus y squared is not the same thing as x plus y. So I do this via an example. If I use x is equal to 1 and y is equal to 2, then if I do 1 squared plus 2 squared and then square root it, I get square root of 1 plus 4, which is equal to square root of 5. But if I just do 1 plus 2, I get 3. Again, these two values are not the same. So therefore, I have found a counterexample for this statement, so it cannot be true. Root of x squared times root of y squared is equal to xy because again we're squaring each term and then square rooting it, which gets us back to the input. So it's the same thing as x times y. And square root of x squared over y squared, again because we can individually square root the numerator and the denominator, then we do get x over y. So just remember, the three statements that are not true are where most people have the misconception. And unfortunately, I've seen under exam conditions, people simplify with Surds incorrectly. So please make sure, remember that these three statements do not hold for all values of x and y, or a and b in some cases. Okay, so let's go through some examples of simplifying. So I need to find an integer such that this expression on the left-hand side can be written as square root of n. So let's look at the first term. 4 root 12 can be rewritten as root 4 times root 3, because 12 is equal to 4 times 3. Root 75 can be rewritten as root 25 times root 3. Now root 4 times root 3 can be rewritten as 2 root 3. And root 25 times root 3 can be rewritten as 5 root 3. If I multiply out the first term, I get 8 root 3, take away 5 root 3, which is equal to 3 root 3. Now some people might stop there, but remember we were trying to write the answer as root n. So 3 root 3 is the same thing as root 9 times root 3, because 3 is the same thing as root 9, which is the same thing as root 9 times 3, which is square root of 27. So in this case, therefore, n is equal to 27. And the next question, we are trying to express root of 22.5 in the form k root 10. So square root of 22.5. Okay, if I had to write it as a integer number, it's the same thing as, as a fraction with the integers in the numerator and the denominator, it would be the same thing as root of 225 divided by 10. Now the rules of Surds tell me that's the same thing as root of 225 over root of 10. Now root of 225 is 15, so I end up getting 15 over root 10. Now I need to rationalize the denominator, so I need to get rid of the square root of 10 in the denominator. So I need to multiply the numerator by root 10 and the denominator by root 10. So what I end up getting is 15 root 10 in the numerator. Root 10 times root 10 is just 10. If I separate out the surd from the numerical part at the beginning, I get 15 over 10 root 10, which can be rewritten as 3 over 2 root 10. Therefore, k is equal to 3 over 2. Okay, let's look at the next examples. Okay, now what happens when we expand these two brackets? Okay, if I expand it, the first term I get is a times a, which is a squared. A times negative b root x gives me negative ab root x. If I do b times b root x times a, I get positive ab root x. And the last term gives me minus b squared root x root x. Now root x, I can simplify that later. But what I do realize is the middle terms do simplify out. So I end up getting a squared, take away b squared, root x multiplies to give you just x. Now if you look at this expression that I've got, there are no surds involved in this expression, which means I started off with expressions involving surds, but I end up with an expression without surds. So this is what we use when we're rationalizing denominators. So when you're rationalizing the denominator, you need to always multiply by the same expression but with the opposite sign in the middle in order to get rid of the surd. Okay, so let's look at an easy example first. So if I have root 5 over root 40 and I need to simplify that surd, the first thing I need to do is think root 40. Because I want to get rid of root 40, I need to multiply the denominator by root 40, but which means I also need to multiply the numerator by root 40. So when I do that, I get root 5 times root 40 over root 40 times root 40. Now in the numerator, I end up getting root of 200 over 40. Root of 200 is the same thing as root of 100 times root of 2 over 40. Which simplifies to 10 root 2 over 40, which is equal to a quarter root 2. Okay, in the second example, it's a bit more complicated. Because I have 4 minus 2 root 3 in the denominator, I need to multiply by the same values but with the opposite sign in the middle. It's the same thing as 6 plus root 3 divided by 4 minus 2 root 3, and to multiply the bottom by 4 plus 2 root 3. So the same thing, numbers, but with opposite sign in the middle. And the same thing to the numerator. So I end up getting that. put brackets around it if it's going to make your life easier, which I end up getting 6 plus root 3 times 4 plus 2 root 3 all over 4 minus 2 root 3 times 4 plus 2 root 3. When I expand the brackets, I get 24 plus 12 root 3 plus 4 root 3 plus 2 times 3. The denominator, I end up getting 4 times 4, which is 16, plus 8 root 3 minus 8 root 3 minus 2 times 2 gives me 4, root 3 times root 3 gives me 3. Now the whole point of multiplying by obviously the same numbers but with the opposite sign in the middle is these two cancels out. So if you don't want to expand the middle terms, you don't have to. So if I simplify, I get 30 plus 16 root 3 all over 16, take away 12, which is 4. If I simplify this, 30 divided by 4 gives me 15 over 2, so I get 15 over 2 plus 16 divided by 4 gives me 4 root 3. So in this case, therefore, A must be equal to 15 over 2 and B must be equal to 4. Okay, now one example where we're problem solving. So we've got this equation and we need to find the answer in the form A plus B root 2. So the first thing I'm tempted to do is expand the bracket. So if I expand the brackets, I get 3 root 2x minus root 2 is equal to 4x plus 6. Okay, when I see this obviously equation in front of me, I need to collect all the x's to one side, all the obviously numerical values to the other side. So if I do that, I get 3 to root 2x minus 4x must be equal to 6 plus root 2. If I factorize the x on the left hand side, I get 3 root 2 take away 4 is equal to 6 plus root 2. X must be equal to 6 plus root 2 divided by 3 root 2 minus 4. So again, when we get an expression, when we get a value like this, we need to rationalize the denominator, which means I need to multiply the top and bottom by 3 root 2 plus 4. It's the same values as the denominator, but with the opposite sign. So when I expand this bracket out, 6 times 3 root 2 gives me 18 root 2 plus 24 plus 3 times root 2 gives me 3 times 2 plus 4 root 2 all over. I only need to think of the first and the last term for the denominator. It gives me 9 times 2 take away 16. Okay, if I collect the like terms, I get 22 root 2 plus 24 plus 6 gives me 30 all over 18 take away 16, which is 2. If I simplify that, I get 11 root 2 plus 15. Therefore, A must be equal to 15 and B must be equal to 11.